your answer is, quote, reasonable. Teachers love to say this. Now, it isn't always possible to judge if an answer is reasonable, but sometimes it is. Certainly in the students and rooms problem, you could see that answers like 1/100th of a room or 90,000 rooms were not reasonable. Also, as I mentioned, you can check your answer. Check it by using proportions or a factor label or a formula or whatever you are inclined to use, but please only use this as a check. And unbelievable as it sounds, that students and rooms problem and two more that we're going to do now will demonstrate much of the quantitative logic that you're going to encounter in virtually every chemistry problem you are ever going to be asked to solve. There are basically only three kinds of problems. You've already done one. 3,000 students in a high school, 30 students per room. How many rooms? 100. Let's try this problem. There are 100 rooms in a high school. There are 30 students per room. How many students are there in that high school? If necessary, pause the video. I suspect you had little difficulty figuring out that if there's 100 rooms in the high school and there's 30 students per room, then the high school is going to contain 3,000 students. But what type of logic underlies this type of solution? The quantity 30 students per room is a this per that. This is true whether the denominator was 1, as it is in this problem, or whether the denominator was 8,735. Anytime you take the quotient of two numbers like these, you are making the denominator 1. This is telling you how many students there are in one room. Now, if there's 30 students in one room, how many students do you think there would be in two rooms? Well, twice as much, obviously. 3 rooms? Well, 3 times as much. 100 rooms? 100 times as much. Now, again, you may look at this and say, I mean, that's pretty simple. But what does that have to do with chemistry? Everything, as I've said before. In chemistry problems, you're going to be given a lot of quantities that are this per that's. Grams per mole, liters per mole, grams per cubic centimeter, moles per liter, whatever. When you see one of these quantities, you must realize that the quotient is telling you how many of the numerator you have for one of whatever is listed in the denominator. So if you have 30 for 1, it's pretty obvious that for 100, you're going to have 100 times as many. Let's look at another problem. A high school has a total population of 3,000 students. There are 100 rooms in that school. How many students are in each room? Well, we've already learned that anytime you need to find out how many of something you have for one of something else, all you have to do is divide the two numbers. And that gives you how many of the numerator you have for one of the denominator. 3,000 students in 100 rooms, 3,000 divided by 100. Dividing those numbers tells you how many students you have in one room, not 100 rooms. If I want to see how many students there are in one room, all I have to do is take the total number of students and divide that by the total number of rooms. That's all there is to it. And whether I take out my calculator, assuming I need one here, or whether I don't, it's the same thing. So let's summarize the major ideas. Almost all introductory chemistry problems are going to involve only two kinds of numbers. What we've called an amount and what we've called a this per that. An amount is a quantity. You visualize it. You visualize it in your mind, a bunch of stuff, so to speak. A this per that with a slash mark or a horizontal line between the quantities tells you how many of the numerator you have for one of the denominator. Let's see if we can apply this logic. We're going to present a problem on the screen. I want you to read the problem, think about it, pause the video, solve the problem, and then watch the solution. The single most important thing is not the answer to this problem. I mean, these are everyday problems. What we're trying to get at is the type of quantitative reasoning that's utilized to solve these kinds of problems. So here's the first problem. A student goes to the candy store with $5. Jelly beans sell for $1.25 per pound. How many pounds of jelly beans can he buy? Now let's take a look at the answer to that problem. The important thing, of course, is not the answer, but the logic. $5 is an amount. You can close your eyes and picture this amount of money. $1.25 per pound tells me how many of these dollars, a bit over one, it takes to buy 1 pound of jelly beans. You look at these two quantities and hopefully you realize that this is a problem just like the first students and rooms problem. $5 is an amount of money. $1.25 per pound is a this per that. And the logic is identical. Students divided by students per room told me the number of rooms. And dollars divided by dollars per pound gives me the number of pounds. Here's another problem. This one is much more involved, so take your time, pause the video, and think carefully before you watch the solution. A car can get 22 miles per gallon of gas. Gas costs $4.88 per gallon. How much will it cost to drive 990 miles? Now this problem is much more involved. And the reason it's more involved is because you cannot solve it in one step. It's going to take 2 steps. Now it's possible that you may have looked at this and immediately saw how to put the numbers together and quickly arrived at the correct answer, $219.60. If you did that, great. But if you didn't, or if you did it but really didn't bother to analyze what you were doing, listen carefully. You're supposed to figure out how much it's going to cost to drive 990 miles. And you're told that gasoline costs $4.88 per gallon. But there's no way to put the quantities 990 miles and $4.88 per gallon together. I mean, they don't fit together. Their units have nothing in common. So before you can figure out how much it's going to cost, you're going to have to figure out how many gallons of gas you're going to have to buy. So the first part of the problem becomes a Gazinta problem. 990 miles. What is that? Is that an amount or is that a this per that? That would be an amount. I hope that's fairly obvious. It's an amount of miles. It certainly can't be a this per that when there's only one unit given, namely miles. This per thats have 2 units separated by a slash mark. But 22 miles per gallon is certainly a this per that. It tells me how many miles we can drive on 1 gallon of gas. Well, if I have to drive a total distance of 990 miles, and 1 gallon of gas will eat up 22 of those miles, then this is another Gazinta problem. How many of these 22-mile packages will consume or Gazinta or use up, use whatever word you like, the 990 miles? And I think if you look at these two numbers, you will realize that it's going to be several gallons. I mean, if you can only go 22 miles on 1 gallon, it's going to take a lot of gallons to go 990 miles. We take out a calculator, we did, and we come up with 45. We're going to have to buy 45 gallons of gas. So how much is it going to cost? Well, let's say gasoline costs $4.88 per gallon. 1 gallon is going to cost just under $5. $4.88 per gallon is a this per that. It tells me how many dollars I need to buy 1 gallon of gas. Well, if it takes this many dollars to buy 1 gallon, how many dollars do you think it would take to buy 2 gallons? Twice as much. And 3 gallons? Well, 3 times as much. And 45 gallons? Well, 45 times as much. If you were able to solve this problem correctly, that's magnificent, because this is our first 2-step problem. And that's not easy for a lot of students. But if you understand the difference between an amount and a this per that, the logic really should begin to fall into place. Let's try another one. The recommended dietary allowance for vitamin C is 60 milligrams per day. If a person sticks to this amount each day, how much vitamin C will they consume in a year? Now, I threw a couple of curveballs at you in this problem. One is psychological. Since the last problem was a two-step problem, many students will assume that this must be a two-step problem. I mean, it's got to be a two-step problem because problems always get harder as we go along, don't they? But this was only a one-step problem. Secondly, you were told how many milligrams of vitamin C were to be consumed each day, but you were not specifically told the number of days that the vitamin C would be taken. Instead, you were told a number of years, 1. Now, you can't put the two things given in the problem, 60 milligrams per day and 1 year, together mathematically. I mean, they don't have anything in common. So you sit down and you say, what is meant by 60 milligrams per day? That tells me how many milligrams of vitamin C I must consume in 1 day. Then, how many milligrams of vitamin C do you think you'd consume in 2 days? Obviously twice as much. 3 days, 3 times as much. Well, what about a year? Well, assuming that you would know that a typical year has 365 days, assuming it's not a leap year. So it's going to take 60 milligrams for 1 day. If that's what it's going to take, then for 365 days, it's just going to take 365 times as much. So I know that the correct way to work this problem is to multiply the two numbers, producing an answer of, I think, 21,900 milligrams per year. Let's try one more. Let's suppose you're walking down the street and a little kid comes up to you and he hands you 4 boxes. And the little kid says that each of these boxes contains 6 marbles. And he says that marbles cost 25 cents each, that is $0.25 per marble. How much do you have to pay the kid to buy all 4 boxes? Now, this problem is somewhat different than any of the other problems we've worked. The reason it's different is that there's no division in this problem. The first thing I have to do is figure out how many total marbles I have to buy. Okay, there's 6 marbles per box. Well, if 1 box contains 6 marbles, then 4 boxes are going to contain 4 times as many. So I have 24 marbles in all. If the marbles only cost 25 cents each, or $0.25 for 1 marble, the 24 marbles are going to cost 24 times as much. You can use a calculator to get the final answer. Perhaps notice that 0.25 is 1/4 of $1, so you have to pay the kid 1/4 of 24 or $6. Now, I don't know if you found these problems simple or difficult, fun or frankly boring, because they were too easy. If you found them to be simple, you might be reasoning that this has nothing to do with chemistry. It has everything to do with chemistry. If you found these problems to be difficult, what does that mean? Well, it actually doesn't mean much of anything, except that you're going to have to go over this logic again. You need to look at this very carefully, really understand exactly what you're doing when you multiply numbers, exactly what you're doing when you divide numbers. Because when you understand that logic, and when you understand what is meant by grams and moles and grams per mole, most of this course becomes just like the students in rooms problems. In the next lecture, we're going to take the same kind of quantitative reasoning ideas and we're going to try to apply them to what might be called a real chemistry situation, namely the concept of density. I would suspect that many of you have probably had density, perhaps in a physical science course, perhaps in your current chemistry course. You may even be able to define density. You may even be able to give me a formula for density. But what is density really? And how does solving density problems relate to the type of quantitative thinking that we've just illustrated with everyday problems? That will be the topic of the next lecture.